In this notebook, we illustrate exploring explainable AI techniques that go beyond SHAP, focusing on integrated gradients and counterfactual explanations. The goal is to better understand not just which features influence the prediction, but also how changing certain inputs could alter the outcome. This is especially important for complex models like neural networks, where traditional methods like SHAP might miss nuances in feature interactions or fail to provide actionable insights. We start by framing the limitations of SHAP. While it effectively quantifies feature contributions relative to a baseline, it does not capture the path-dependent nature of neural network decisions or offer clear guidance on what changes could flip a prediction. Integrated gradients address this by attributing importance along the actual input path, providing a more faithful explanation for deep models. Counterfactual explanations complement this by identifying minimal changes needed to reverse a prediction, which is crucial for understanding model behavior in real-world scenarios like customer churn. The walkthrough uses a realistic churn prediction model to demonstrate these techniques end-to-end. First, integrated gradients will highlight which features drove a particular prediction, showing their relative importance as the model processes the input. This helps us see not just which features matter, but how their influence accumulates through the network layers. Next, we apply counterfactual explanations to answer a different question. What specific feature adjustments would change the model-agnostic decision from churn to retention? This provides actionable insights, potentially guiding interventions or business strategies. As you follow along, watch for how integrated gradients produce attribution scores that reflect the model-agnostic's internal computations, offering a nuanced view beyond static feature importance. Then, observe how counterfactuals generate plausible alternative scenarios, revealing the sensitivity of predictions to input changes. Together, these methods give a richer, more actionable understanding of model behavior than SHAP alone, making them valuable tools for interpretable AI in practice. We start by importing essential libraries for data manipulation, machine learning, and deep learning. These include NumPy and Pandas for data handling, scikit-learn for preprocessing and evaluation, and PyTorch for building and training neural networks. This setup is crucial as it provides the foundational tools needed to generate data, train models, and assess their performance efficiently. Next, we define a custom wrapper class around a PyTorch model to make it compatible with scikit-learn's interface. This class implements the fit, predict, and predict-proba methods, enabling seamless integration with scikit-learn utilities like cross-validation and scoring functions. The predict-proba method converts model outputs to probabilities using a sigmoid activation, which is essential for binary classification tasks such as credit risk prediction. The core of our data generation lies in the make credit risk data function, which synthesizes a realistic credit risk dataset. It simulates borrower and loan features like credit score, income, debt-to-income ratio, loan-to-value ratio, and others, using distributions that mimic real-world ranges and behaviors. For example, credit scores are normally distributed around 690 with bounds to reflect typical credit score limits, while income follows a long normal distribution to capture skewness in earnings. A key aspect of this synthetic data is the calculation of a true default probability through a complex logistic model. This model incorporates nonlinear effects and feature interactions, such as the strong negative impact of low credit scores on default risk, the combined effect of high debt-income ratio and high credit utilization, and the influence of loan-to-value ratio, especially when credit score is low. The inclusion of noise and categorical effects like region and home type adds realism, making the dataset a challenging yet instructive benchmark for modeling. Once the dataset is generated, we split it into training and test sets with stratification to preserve the default rate distribution. We then standardize the features using scikit-learn's standard scaler to ensure that all inputs have zero mean and unit variance. This step is vital for neural network training, as it stabilizes and accelerates convergence by preventing features with large scales from dominating the learning process. The architecture consists of an input layer matching the number of features, two hidden layers with 64 and 32 neurons respectively, ReLU activations for nonlinearity, and a dropout layer to mitigate overfitting. The final layer outputs a single logit per instance, which will be converted to a probability for classification. This design balances model capacity and regularization, making it suitable for tabular data like credit risk features. We prepare the data tensors for PyTorch by converting the standardized NumPy arrays into float 32 tensors on the specified device, which is CPU in this case. The target labels are also converted to float tensors to match the expected input for the binary cross-entropy loss function. This preparation ensures compatibility between data and model during training. The training loop runs for 10 epochs, using mini-batches of size 512 to efficiently compute gradients and update model weights. For each batch, we zero the gradients, perform a forward pass to compute logits, calculate the binary cross-entropy loss with logits, backpropagate to compute gradients, and take an optimizer step with atom. The weight decay parameter adds L2 regularization, helping to prevent overfitting by penalizing large weights. After training, we switch the model to evaluation mode and compute predicted probabilities on the test set by applying the sigmoid function to the model outputs. We then calculate the ROCAUC score, a robust metric for binary classification that measures the model's ability to distinguish between default and non-default cases across all classification thresholds. The printed ROCAUC value provides a concise summary of model performance, indicating how well the MLP captures the complex relationships in the synthetic credit risk data. Interpreting the ROCAUC score, values closer to 1 indicate excellent discrimination, while 0.5 corresponds to random guessing. Given the complexity and noise in the synthetic data, a high ROCAUC suggests that the model has successfully learned meaningful patterns and interactions among features, validating both the data generation process and the neural network's capacity to model nonlinear relationships in tabular data. In this cell, we define and apply the integrated gradients method to explain the model's prediction for a single test example. Integrated gradients is a powerful interpretability technique that attributes the prediction to each input feature by integrating gradients along a path from a baseline input to the actual input, providing a principled way to measure feature importance. The function integrated gradients takes the trained model, an input tensor x, an optional baseline tensor, and the number of steps for the integration path. If no baseline is provided, it defaults to a zero tensor matching the input shape, representing a neutral reference point. The core idea is to approximate the integral of gradients by summing gradients computed at evenly spaced points along the straight line between the baseline and the input. First, the function sets the model to evaluation mode to ensure consistent behavior during attribution. Then, it creates a sequence of interpolation coefficients, alphas, ranging from 0 to 1, with shape steps 1. These coefficients scale the difference between the input and baseline, generating a path x path of shape steps, d, where d is the input dimension. This path represents intermediate inputs starting at the baseline and ending at the actual input. By enabling gradient tracking on x path, the function computes the model's output logits for each interpolated input. Since integrated gradients requires a scalar output to differentiate, it sums the logits across all steps, producing a scalar s. Then, it calculates the gradients of s with respect to x path, resulting in a tensor of gradients with shape steps, d. To approximate the integral, the function averages these gradients over all steps, yielding AVG grads, a vector representing the mean sensitivity of the output to each input feature along the interpolation path. Finally, it multiplies this average gradient by the difference between the input and baseline, producing the integrated gradients attribution vector IG. This vector quantifies how much each feature contributed to the change in prediction from the baseline to the actual input. Next, we select the first test example x0 from the test dataset xDE, making a detached clone to avoid any side effects. We compute the model's predicted default probability for this example by applying the sigmoid function to the model's raw output logits, printing this value to provide context for the attribution. We then call the integrated gradients function with x0, using a 0 baseline and 96 integration steps for a finer approximation. The resulting attribution vector IG0 is converted to a NumPy array on the CPU for easier manipulation. To interpret these attributions, we construct a pandas data frame local IG that pairs each feature name with its corresponding integrated gradients value and the absolute value of that attribution. Sorting this data frame by the absolute attributions in descending order highlights the features that most strongly influence the model's prediction for this specific example. Finally, we print the top 10 features with the highest absolute integrated gradients attributions. These features represent the most critical drivers of the model's decision for this input, offering valuable insights into the model's reasoning and helping to build trust or identify potential biases. By examining these attributions, one can understand which features push the prediction higher or lower relative to the baseline, facilitating explainability in complex models. In this cell, we define a function to compute the global integrated gradients IG ranking for our model's features. The function samples a subset of the test data, calculates the absolute IG values for each sample, and averages them to get a global importance score per feature. This approach helps us understand which features consistently have the most influence on the model-agnostic predictions across many examples. The function starts by randomly selecting a subset of samples from the input tensor, ensuring reproducibility with a fixed seed. For each chosen sample, it computes the integrated gradients relative to a zero baseline, accumulating the absolute values of these attributions. After processing all samples, it stacks the results into a 2D array and averages across samples to get a mean absolute attribution per feature. We then call this function on our test dataset with 1,200 samples and 64 integration steps, which balances computational cost with attribution accuracy. The results are stored in a data frame alongside feature names and sorted in descending order of mean absolute IG. Printing the top 10 features reveals which inputs the model relies on most strongly in general, providing valuable insight into its decision-making process. When interpreting the output, look for features with the highest mean absolute IG value as zeros. They represent the most influential predictors according to the integrated gradients method. This global perspective complements local explanations by summarizing feature importance across many instances, which is crucial for validating model behavior and identifying key drivers in the data. In this cell, we perform a sanity check on our model using permutation importance, which is a model-agnostic method to estimate feature importance. First, we define a helper function that wraps our PyTorch model to behave like a scikit-learn predict proba method, taking standardized NumPy arrays as input and outputting predicted probabilities. This step is crucial because permutation importance expects a model interface compatible with scikit-learn, so wrapping our model allows us to integrate it smoothly. Next, we create a custom scoring function based on the area under the curve AUC metric, which measures the model-agnostic's ability to distinguish between classes. The awkscore function takes an estimator, input features, and true labels, then returns the AUC score computed from predicted probabilities for the positive class. Using AUC as the scoring metric is important here because it provides a threshold-independent evaluation of model performance, making it well-suited for binary classification tasks. We then call permutation importance from scikit-learn, passing our wrapped model, the standardized test set, true labels, and the AUC scorer. We specify 5 repeats to get a stable estimate and set a random seed for reproducibility. The permutation importance method works by randomly shuffling each feature column in the test data and measuring how much the model-agnostic's AUC score decreases. Features that cause a larger drop in AUC when permuted are deemed more important, as shuffling them disrupts the predictive signal. After computing the permutation importance, we organize the results into a data frame, pairing each feature name with its mean importance score across repeats. Sorting this data frame in descending order highlights the top features that most influence the model-agnostic's predictive performance. Printing the top 10 features gives us an interpretable summary of which inputs the model relies on most heavily. When you look at the output, watch for features with the largest positive permutation importance value as zeros. These indicate the features whose randomization most degrades model performance. Features with near zero or negative importance suggest they have little to no impact or might even add noise. This step serves as a sanity check because it confirms whether the model-agnostic's learned patterns align with domain knowledge or expected feature relevance. Overall, this approach provides a transparent, model-agnostic way to validate feature importance and helps ensure that our model-agnostic's predictions are driven by meaningful input variables rather than spurious correlations. In this section, we implement a method to find minimal changes to an input example that can flip a model-agnostic's decision from high risk to lower risk. This is called generating a counterfactual, which is crucial for interpretability and actionable insights. Showing what small, feasible adjustments could improve an applicant's predicted risk profile. We start by defining which features are immutable, like age, region, and home type, meaning these cannot be changed in the counterfactual. We also mark some features as semi-mutable, such as employment years, which we allow to change but penalize heavily to discourage unrealistic jumps. This distinction is important because it respects real-world constraints and ensures the counterfactuals are plausible. Next, we create mappings from feature names to their indices in the feature vector, so we can easily access and manipulate specific features during optimization. We separate indices into immutable, semi-mutable, and mutable groups. This setup is key for applying different constraints and penalties during the optimization process. We define bounds for each feature in the original, unscaled space. These bounds reflect realistic limits for each variable, such as credit score between 520 and 850 or income between 15,000 and 500,000. Keeping changes within these bounds ensures the counterfactuals remain plausible and actionable. The function project to bounds takes a feature vector in the original space and clips each feature to its allowed bounds. It also rounds categorical and count features to the nearest integer to maintain valid data types. This projection step is critical because gradient-based optimization can push values outside realistic ranges, and we need to bring them back to feasible regions. The core function counterfactual performs gradient-based optimization to find a counterfactual example close to the original input, but with a predicted probability below a target threshold, indicating lower risk. It starts by scaling the original input using the same scalar as the model, then initializes a tensor with gradients enabled for optimization. We assign weights to features to control how much they can change. Immutable features get an extremely high weight, effectively freezing them, while semi-mutable features get a moderate penalty. Mutable features have a default weight of 1, allowing them to change more freely. This weighting scheme guides the optimizer to find realistic, minimal changes. The optimizer used is Atom, a popular choice for gradient-based methods due to its adaptive learning rates. We define a target logit corresponding to the desired maximum risk probability, converting from probability space to logit space since the model outputs logits. The optimization loop runs for a fixed number of steps. In each iteration, we compute the model-layer logit for the current candidate input and calculate a constraint loss that penalizes logits above the target. We add a proximity loss, which is a weighted L1 distance from the original input, encouraging minimal changes. After computing gradients, we explicitly zero out gradients for immutable features to keep them fixed. Then the optimizer updates the candidate input. To maintain feasibility, we project the candidate back to valid bounds in the original space, then rescale it for the next iteration. This projection after each step prevents drifting into unrealistic feature values. We check every 25 steps if the predicted probability meets the target threshold and stop early if it does. This early stopping saves computation and returns the first feasible counterfactual found. Finally, the function returns the counterfactual example in the original feature space, clipped and rounded appropriately. This output can be compared to the original input to understand what minimal changes reduce the predicted risk. To demonstrate, we select the highest risk example from the test set by finding the index with the maximum predicted probability. We extract its feature vector and predicted risk. Displaying this example sets the stage for generating a counterfactual and interpreting what changes could flip its risk assessment. Overall, this approach combines domain knowledge about feature mutability, realistic bounds, and gradient-based optimization to produce actionable counterfactuals. These counterfactuals help users understand the model-layer decision boundaries and identify feasible ways to improve outcomes. In this cell, we generate a counterfactual example for a given input, x high, by adjusting its features to reduce the model's predicted probability to 0.30 or less. The counterfactual function iteratively modifies the input over 500 steps with a learning rate of 0.06 and a regularization term of 0.02, balancing the goal of lowering the prediction with keeping changes minimal and realistic. This process is crucial because it helps us understand what minimal changes to the input could lead to a significantly different model decision, offering insights into model behavior and potential actionable interventions. Next, we create pandas series for the original input before and the counterfactual after, both indexed by feature names, and calculate their difference delta. This step highlights which features changed and by how much, allowing us to pinpoint the key drivers behind the shift in prediction. We then scale the counterfactual using the same scalar applied during training to ensure consistency before passing it to the model for a new probability prediction, PCF. This confirms that the counterfactual indeed achieves the target probability threshold, validating the effectiveness of the perturbations. To make these changes interpretable, we assemble a data frame, CFDF, that lists each feature alongside its original value, counterfactual value, and the delta. We filter out negligible changes to focus only on meaningful shifts and sort them by the absolute magnitude of change. Displaying this data frame lets us quickly identify which features were most influential in driving the prediction down to the target probability, providing actionable insights or hypotheses about feature importance in this specific context. Following the counterfactual analysis, we refit the model wrapped in a torch wrapper to ensure compatibility with scikit-learn utilities. This wrapper is necessary because the permutation importance function expects an estimator with a scikit-learn interface. Using the test set, We then compute permutation importance with 5 repeats, scoring by ROZ-AUC. This method measures how shuffling each feature affects model performance, revealing the global importance of features and predicting the outcome. The printed results show the mean importance and standard deviation for each feature, helping us understand which features the model relies on most across the entire dataset. Together, these steps provide both a local explanation euros through the counterfactual example euros and a global perspective euros via permutation importance euros on how the model uses features to make predictions. This dual approach is powerful for diagnosing model behavior, validating assumptions, and guiding feature engineering or decision-making processes. Here, we start by importing Plotly Express and Pandas, essential for data manipulation and visualization. We set a variable to focus on the top 12 features, which helps us zero in on the most important predictors without overwhelming the plot. Next, we extract the top features from 2 different importance metrics, integrated gradients and permutation importance. Each subset contains the feature names and their corresponding importance scores. By merging these 2 subsets on the feature names, we create a combined data frame that includes all top features from both methods, filling any missing values with 0 to ensure completeness. We then reshape this combined data frame from a wide to a long format using the melt function. This step is crucial because it prepares the data for Plotly Eurostrade S grouped bar chart, where each feature will have side-by-side bars representing the 2 importance metrics. The melted data frame has columns for the feature name, the type of metric, and the importance value, making it easy to plot. The visualization itself is a horizontal grouped bar chart, which sorts the bars by importance value in ascending order. This sorting helps us quickly identify which features have higher or lower importance across both metrics. The bars are color-coded by metric, allowing us to compare integrated gradients and permutation importance side by side for each feature. The Plotly Eurostrade S size and title are set to ensure clarity and context. When you look at the output, pay attention to how the importance scores differ or align between the 2 methods. Features with consistently high importance in both metrics are likely strong predictors, while discrepancies might indicate differences in how each method interprets feature impact. This comparison is valuable for validating model explanations and gaining deeper insights into feature relevance. Here, we create a horizontal waterfall chart using Plotly to visualize the top 12 local integrated gradients attributions from the dataset. First, we select the top features based on their attribution scores and reverse their order so the most impactful feature appears at the top of the chart. This ordering helps make the visualization intuitive, showing how each feature contributes incrementally to the model's output. The waterfall plot uses the feature names on the y-axis and their corresponding attribution values on the x-axis, with each bar representing the relative contribution of a feature to the logit score. We format the attribution values with plus or minus signs to clearly indicate positive or negative impacts. This directional information is crucial for interpreting whether a feature pushes the prediction higher or lower. By setting the orientation to horizontal and customizing the layout size, the chart becomes easier to read, especially when dealing with many features. The title explicitly states that these are local integrated gradients, emphasizing that the attributions are specific to a single prediction rather than global feature importance. When you view the output, look for which features have the largest positive or negative bars, as these are the key drivers influencing the model's decision for this particular instance. Overall, this visualization provides a clear, step-by-step breakdown of how individual features affect the model's output, making it a powerful tool for model interpretability and debugging. Here, we create a scatter plot showing the relationship between credit scores and predicted default probabilities on the test set. This visualization helps us understand how the Model Eurostrade S predicted risk changes with credit score values, revealing any trends or patterns. Using a smooth lowest trend line highlights the overall risk trajectory, making it easier to spot nonlinear effects. The Plotly Eurostrade S size is adjusted for better readability, ensuring the insights are clear when we view it. In this cell, we start by selecting a random sample of 300 data points from the test set to compute integrated gradients IG attributions without excessive computation. We use a fixed random seed to ensure reproducibility when picking these indices. For each selected data point, we clone the input tensor and calculate the IG values relative to a baseline of zeros, using 64 steps for the integral approximation. This step-by-step accumulation of gradients helps us understand how each feature contributes to the Model Eurostrade S prediction for that specific input. After computing IG for all sample points, we stack these arrays vertically into a single matrix, then convert it into a pandas data frame with feature names as columns. To facilitate visualization, we reshape the data frame from wide to long format using the melt function, which creates 2 columns, one for feature names and one for their corresponding IG values. This transformation is crucial for plotting as it allows us to compare the distribution of attributions across features more easily. Next, we filter this long data frame to include only the top 8 features identified previously in the global IG summary. This focus on the most important features ensures the plot remains readable and highlights the key drivers behind the model-agnostic decisions. The filtered data is then passed to Plotly Express to create a box plot, which displays the distribution of IG attributions for each feature across the sampled borrowers. The inclusion of outliers as individual points helps reveal variability and potential edge cases in feature importance. We also customize the plot-agnostic layout by setting the width and height for better visibility, especially when dealing with multiple features. Finally, the plot is rendered inline, showing how the attributions vary across the sample. This visualization is essential for interpreting the model-agnostic behavior. It reveals not just which features are important on average, but how their influence fluctuates across different instances, providing deeper insights into model explainability. This table compares when integrated gradients IG outperform SHAP for model explanations. IG is better for deep neural networks because it uses true gradients, providing more accurate attribution. It also excels in time series models by preserving temporal structure, which SHAP might disrupt. For highly nonlinear models, IG avoids the sampling noise that can affect SHAP-agnostic estimates. Lastly, IG offers theoretical guarantees like the completeness property, ensuring the attributions sum to the model output, which is important for trustworthy explanations. This table summarizes when to use different explanation methods for machine learning models. It highlights SHAP for consistent global insights across any model, integrated gradients for faithful attributions in neural networks, and counterfactuals for actionable recommendations in decision support. Understanding these strengths helps choose the right tool for interpreting your model-agnostic behavior effectively. This cell marks the end of the notebook or script, signaling that all processing or analysis is complete. Data-agnostic is a simple way to indicate that no further code will run beyond this point, helping to keep the workflow organized and clear. This is especially useful in longer nopes to show where the final output or conclusion lies.